Hello everyone, my name is Neha Balakrishna and today I'll be presenting the second portion of the Charged Tapes lab. The main objective of this lab was to create a computational model of two charged tapes exerting an electric force on each other, and from this model we were to estimate the net charge on each tape by modeling each tape as a line charge. So key concepts and equations in this lab. One important concept is Coulomb's law, which essentially states that the electric force is proportional to the charge of objects interacting and inversely proportional to the distance r between them. In addition, Newton's second law is important as there are two forces acting on the tape, electrical and gravitational, during the experiment. Because the top tape is in equilibrium and therefore does not experience a change in momentum, it can be said that the net force is zero and equal to the vector sum of the electric and gravitational forces. Now I'm going to briefly summarize the results of the previous lab where we modeled the tapes as point charges. So in part 1 of the previous lab, the main objective was to prepare the charged U tapes using the experiment. And I did this by creating a base tape, sticking a U tape on the base tape, and then quickly ripping the U tape off. I ensured that there was no charge transfer from the tape by putting it aside carefully and handling it only by its ends. So this next part focused on quantitatively determining the U tape's charge. So to determine if the tape was charged properly to begin with, I made sure that the U-tapes were attracted to my hand, and then I could determine whether the charges on the U-tape were like or opposite, and because they repelled each other, they had the same sign charge. The last step was to determine whether the U-tapes were both positively charged or negatively charged, and because they were attracted to a negatively charged pen, I concluded that they were positively charged. In the last part of the experiment, I was to quantitatively determine the U-tape's charge. In order to do this, I suspended one of the U-tapes a height above my working surface by attaching each end to objects of the same height. Then I held the second U-tape underneath the first U-tape and brought it closer to the first U-tape until it began to float, indicating the presence of an electric force on the tape. I recorded the distance between the two tapes when this phenomenon was observed. So I had to make the assumption that each of the U-tapes had the same charge, and I also had to treat each U-tape as a single point charge to simplify calculations of the electric force exerted on the U-tape. Additionally, I observed during the experiment that the top U-tape began floating when it was a vertical distance of 0.015 meters from the bottom tape. So, using these observations, I was able to calculate various quantities. Because the tape was in equilibrium, I set the electric force equal to -1 times the gravity force. And rearranging Coulomb's law, I was able to write an equation for Q and calculate it to be 7 times 10 to the -9 coulombs for the point charge model. So that was just a brief summary of the previous lab where we modeled the tapes as point charges, but now I'm going to discuss how the calculated charge would change if we modeled the tapes as line charges. Before creating this model, I had to make some assumptions and approximations. Like the previous lab, I assumed that each U-tape had the same net charge and that the effect of air resistance on the tapes in equilibrium could be ignored. However, in this lab uniquely, I treated each U-tape as a line charge with a uniform distribution of charge and therefore decided to model the charge tape by dividing it into 35 chunks of tape in my glow script model. I also made sure to ignore the interactions between charges on the same tape. So here's the code for the computational model I created in glow script. I defined key constants in quantities at the beginning, including gravity, the K constant, and the mass of the tape. I also wrote a function to calculate the vector electric field on each chunk dq of the top tape exerted by each chunk dq of the bottom tape. I then was able to use this function in a for loop to calculate the net E field on each dq chunk in the top tape by summing the vector E fields at its location created by the dq chunks of the bottom tape. For each dq chunk in the top tape, I calculated the electric force by multiplying its charge dq by the net electric field dE at its location. So here is the computational model that the code ended up creating. So the line of red spheres B represents the top tape, and the line of blue spheres A represents the bottom tape. And you can clearly see that at each dq chunk on the top tape, there is an E field, and adding all of these individual E fields acting on each dq chunk calculates the net electric field on the entire top tape B due to the entire bottom tape A. I determined the charge on each tape by trial and error until the program printed out the same value for the magnitude of the electric force and gravitational force. So what if the charge tapes were modeled as a point charge? Like I discussed earlier, the charge of the tape determined using the point charge model was 7 times 10 to the -9 coulombs, while the charge on the tape determined using the line charge model was 1.90174 times 10 to the -8 coulombs. And this essentially means that the tape charge as calculated with the line charge model was 2.71 times the charge of the tape calculated with the point charge model. And this illustrates that the point charge model likely underestimated the actual amount of charge on the tape. I explained earlier how the net electric field is calculated for the top tape in the line charge model. And because some chunks in the bottom tape are farther from each DQ in the top tape than others, each DQ chunk in the bottom tape has a different field contribution at each location of the DQ chunks in the top tape. So we can therefore conclude that when two point charges with Q1 and two line charges with Q2 are separated by the same distance in equilibrium, Q2 would need to have a greater magnitude, similar to how the tape was calculated to have a greater charge using the line charge model. We can also conclude that the line charge model is more accurate because it models a distribution of charge over a length which better represents the charge distribution on the tape, as not all of the net charge on the tape is concentrated at one spot on the tape, as the point charge model suggests.